Welcome to this coding problem walkthrough. In this session, we'll explore problem number 1955, count number of special subsequences. We'll break down the problem, examine different approaches, and guide you step by step toward an optimal solution. Let's dive in. In this problem, we are tasked with counting the number of special subsequences in a given integer array. A subsequence is defined as special if it is derived from the array 0, 1, 2, and adheres to the specific order of 0-1-2. This means that the subsequence must include at least one 0, followed by at least one 1, and then at least one 2, and these numbers must appear in this exact sequence, though they do not need to be consecutive. The goal is to determine how many such special subsequences can be found in the input array, and we are required to return the answer modulo 10⁻9 plus 7 to handle potentially large results. The input is an array of integers limited to 0, 1, and 2, and the output is a single integer representing the count of special subsequences. For example, if the input array is 0, 1, 2, 0, 1, 2, the output is 7. This is because there are 7 distinct special subsequences that can be formed, following the order of 0-1-2. These include subsequences like 0, 1, 2, formed by taking the first 3 elements, or 0, 1, 2, formed using indices 0, 4, and 5, among others. Each valid subsequence maintains the required order, and the indices used to form them are unique in each case. Similarly, if the input is 0, 1, 2, 2, the output is 3, as there are 3 special subsequences possible here: 0, 1, 2, using indices 0, 1, 2, 0, 1, 2, from indices 0, 1, 3, and 0, 1, 2, using indices 0, 2, 3. Now consider the input 2, 0, 1. In this case, the output is 0, as there are no valid special subsequences. Although the array contains all 3 numbers 0, 1, and 2, the required order of 0-1-2 is not followed. This highlights the importance of maintaining the sequence order when identifying special subsequences. Additionally, the problem comes with constraints to ensure that it can handle large input sizes efficiently. For instance, the length of the input array can be as large as 10⁻5, meaning the solution must be optimized for performance. The values in the array are restricted to 0, 1, and 2, which simplifies the problem space. However, edge cases need to be considered. For example, if the array is missing any of the required numbers, such as no 0s, no 1s, or no 2s, the output must be 0 since a special subsequence cannot be formed. Similarly, if the array is already sorted in the form of repeating 0, 1, 2, we must ensure all valid subsequences are counted. On the other hand, if the numbers appear in reverse order or are entirely out of sequence, the output should also be 0. Handling these scenarios efficiently is key to solving the problem correctly, even when the array size is at its maximum limit. To begin solving this problem, let's first consider a brute force approach and its intuition. The idea here is to generate all possible subsequences of the input array and then check each one to see if it qualifies as a special subsequence. A subsequence is considered special if it contains the elements 0, 1, and 2 in that exact order, though they don't need to be contiguous. This would involve 2 major steps: first, generating all subsequences of the array, which takes exponential time since there are 2 to the power of n subsequences for an array of size n, and second, examining each subsequence to ensure it has at least one 0 followed by at least one 1 and then a 2. While this method is conceptually straightforward, the key limitation is its inefficiency. The exponential growth of subsequences makes it completely impractical for larger arrays, as the time complexity quickly becomes unmanageable. This approach is only suitable for very small inputs due to its computational overhead. To address the inefficiency of the brute force method, we turn to an optimized dynamic programming approach. Instead of generating all subsequences, we aim to track the counts of valid subsequences as we process the array. To do this, we define 3 states: count_0, which keeps track of the number of subsequences ending in 0, count_1, which counts the subsequences ending in 1 that were formed by extending the subsequences in count_0, and count_2, which counts the subsequences ending in 2 that were formed by extending those in count_1. The transitions between these states follow specific rules. When encountering a 0, it can either start a new subsequence or extend an existing one ending in 0, so count_0 is updated as 2 times itself plus 1. For a 1, it can extend any subsequence in count_0, so count_1 becomes 2 times itself plus count_0. Similarly, for a 2, it can extend any subsequence in count_1, so count_2 becomes 2 times itself plus count_1. These updates ensure that we only maintain running counts of valid subsequences without explicitly enumerating them. To handle large inputs, we take modulo 10 to the power of 9 plus 7 at each step, ensuring our calculations remain manageable. The result of our dynamic programming approach is stored in count_2, as it represents the number of special subsequences that meet the required condition of ending in 2. The implementation is efficient, with a time complexity of O(n), where n is the size of the array, because we process each element exactly once. The space complexity is constant, or O(1), since we only use a few variables to store the counts. This makes the DP solution not only optimal but also highly scalable. By leveraging the sequential dependency of special subsequences, where 0 must appear before 1, and 1 before 2, we avoid the need to generate all subsequences. This efficiency is crucial for handling scenarios with large input sizes. The dynamic programming approach was chosen because it strikes the perfect balance between clarity, efficiency, and scalability. It transforms what would have been an exponentially complex problem into one that runs in linear time with constant space. This makes it the only viable solution for large inputs where the size of the array, n, can go up to 100,000. While the brute force approach is simpler to conceptualize, its inefficiency renders it impractical for competitive programming or real-world applications. The DP solution, on the other hand, is not only optimal but also robust and well-suited for scenarios where performance is critical. In this problem, we are tasked with finding the number of subsequences in an array that contain the elements 0, 1, and 2 in strict order. A subsequence is formed by selecting some or all elements of the array while preserving their relative order. A brute force approach involves generating all possible subsequences of the array using recursion or bit masking. For an array of length n, this would result in 2n subsequences. Once all subsequences are generated, we need to check each one to see if it contains 0, 1, and 2 in the correct order. This can be done by iterating through each subsequence and ensuring that 0 appears before 1, and 1 appears before 2. We then keep a counter to track all subsequences that satisfy this condition. Finally, we return the total count of valid subsequences. While this approach is straightforward, it is computationally expensive due to the exponential growth in the number of subsequences as n increases. The brute force approach, while conceptually simple, is highly inefficient. Generating all subsequences takes O(2 to the power of n) time, and checking each subsequence for validity requires O(n) in the worst case. This results in a total time complexity of O(2 to the power of n*n), which becomes infeasible for large arrays. To overcome this, we can use dynamic programming to optimize the solution. Instead of explicitly generating all subsequences, we can count valid subsequences directly in a single pass through the array. The key idea is to define state variables that represent cumulative counts of subsequences meeting specific criteria. For instance, count_0 tracks subsequences ending with 0, count_01 tracks subsequences ending with 1 that include at least one 0, and count_012 tracks subsequences ending with 2 that include at least one 0 and 1 in the correct order. By maintaining these counts as we traverse the array, we avoid the exponential blowup of generating all subsequences. Initially, all state variables are set to 0. As we process each element in the array, we update our state variables dynamically. If the current element is 0, we increment count_0 by 1 because each 0 can form a new subsequence. If the element is 1, we update count_01 by adding the value of count_0. This is because any subsequence ending with 0 can now be extended to include this one. Similarly, if the element is 2, we update count_012 by adding the value of count_01, since all subsequences ending in 01 can now be extended to include this too. By the time we finish iterating through the array, count_012 will hold the total number of valid subsequences that meet the problem's criteria. This approach is highly efficient, with a time complexity of O(n), since we make a single pass through the array. Additionally, the space complexity is constant, O(1), as we only use 3 counters to track our state variables. The optimized dynamic programming approach offers several key insights. First, it avoids the computational expense of generating all subsequences explicitly. Instead, it directly counts valid subsequences as the array is processed. This eliminates the exponential time complexity of the brute force method. Second, the problem's requirement for a strict order of 0, 1, and 2 without needing the elements to be contiguous allows us to use cumulative counts to track subsequences efficiently. This means we only need to ensure the relative order of elements, which is elegantly handled by the state variables. Finally, the use of dynamic programming with three counters count_0, count_01, and count_012 encapsulates the subsequence requirements while maintaining constant space usage. This approach not only optimizes performance but also simplifies the implementation by using minimal data structures. To better understand the dynamic programming solution, let's walk through an example with the input array 0, 1, 2, 0, 1, 2. We start by initializing our counters. Count_0, count_01, and count_012 are all set to 0. Processing the first element, 0, we increment count_0 to 1 because we can form a new subsequence with this 0. Next, for the element 1, we update count_01 to 1 since we can extend the subsequence ending with 0 to include this one. For the element 2, we update count_012 to 1 as the subsequence 01 can now be extended to include this too. Processing the second 0, we increment count_0 to 2. For the next one, count_01 becomes 3 because both subsequences ending with 0 can be extended. Finally, for the last two, count_012 becomes 4, as all three subsequences ending with 01 can be extended. The final value of count_012, which is 4, represents the total number of valid subsequences. When implementing this solution, it's important to consider edge cases. For example, if the input array contains no 0, 1, or 2, such as 3, 4, 5, the output will be 0 because no valid subsequences can be formed. If all elements in the array are the same, such as 0, 0, 0, the output will also be 0 since the required elements 1 and 2 are missing. For a minimum length array like 0, 1, 2, the output is 1 because there is only one valid subsequence. At the end of the traversal, the value stored in count_012 represents the total number of valid subsequences, providing the final result. This approach is both efficient and robust, handling all edge cases while maintaining optimal performance. This solution efficiently calculates the number of special subsequences using a dynamic programming approach. We maintain three counters, count_0, count_1, and count_2, which represent the number of valid subsequences ending with 0, 1, and 2, respectively. ##explanation. 1. Initialization. Count_0, count_1, and count_2 are initialized to 0, as initially, there are no subsequences. 2. Iterating through the array. For each 0, it can either start a new subsequence or extend existing subsequences ending with 0. The new count for count_0 is 2 count_0 plus 1, where the 1 represents the new subsequence starting with the current 0. For each 1, it can extend existing subsequences ending with 0, forming subsequences like 0-1, or extend existing subsequences ending with 1. Hence, count_1 is updated as 2 count_1 plus count_0. For each 2, it can extend subsequences ending with 1, forming subsequences like 0-1-2, or extend existing subsequences ending with 2. Thus, count_2 becomes 2 count_2 plus count_1. 3. Modulo operation. Since the result can be very large, all updates are taken modulo 10⁻9 plus 7. For final output, at the end of the loop, count_2 contains the total number of special subsequences that satisfy the conditions. ##complexity. Time complexity, O(n), where n is the length of the input array. We iterate through the array once. Space complexity, O(1), as we only use 3 variables to store the counts, regardless of the input size. This approach is optimal and ensures the solution is computed efficiently even for large inputs. This is the Java implementation of LeetCode problem number 1955, count number of special subsequences. The logic mirrors the Python implementation, with type declarations and Java syntax. The method iterates through the input array, maintaining counts for subsequences ending with 0, 1, and 2, using modular arithmetic to handle large numbers. The result is returned as an integer. To solve this problem, we start by initializing three counters, count_0, count_1, and count_2, all set to 0. These counters will track the number of valid subsequences ending with 0, 1, and 2 respectively. We also define mod as 10 to the power of 9 plus 7 to ensure we handle large numbers within the constraints. Looking at the first example, nums equals 0, 1, 2, we process each number step by step. The first number is 0. Each occurrence of 0 can either start a new subsequence or extend existing subsequences that already end in 0. Using the formula count_0 equals 2 asterisk count_0 plus 1 %mod, we calculate count_0 as 1. The second number is 1. Each one can extend subsequences that end in 0 or extend subsequences already ending in 1. This is calculated using the formula count_1 equals 2 asterisk count_1 plus count_0 %mod, resulting in count_1 being updated to 1. Finally, the third number is 2. Here, each 2 can extend subsequences ending in 1 or subsequences already ending in 2. Using the formula count_2 equals 2 asterisk count_2 plus count_1 %mod, count_2 becomes 1. At the end of this process, all three counters are 1, and the resulting output is stored in count_2. After completing the first example, we find that the final output is count_2 equals 1, which means there is one special subsequence for nums equals 0, 1, 2. Now, consider the second example, nums equals 0, 0, 1, 2, 2. Again, we start with all counters initialized to 0. The first number is 0, so we calculate count_0 equals 2 asterisk count_0 plus 1 %mod, resulting in count_0 being updated to 1. When we encounter another 0, we repeat the same calculation, but now with the updated value of count_0. This gives us count_0 equals 3. Moving on to the third number, 1, we compute count_1 equals 2 asterisk count_1 plus count_0 %mod. Since count_0 is 3 and count_1 was initially 0, this updates count_1 to 3. The fourth number is 2, and using the formula count_2 equals 2 asterisk count_2 plus count_1 %mod, we find that count_2 becomes 3 as well. At this point, the state of the counters is count_0 equals 3, count_1 equals 3, and count_2 equals 3. Now we process the fifth and final number in this example, which is another 2. Using the same formula for 2, count_2 equals 2 asterisk count_2 plus count_1 %mod, and substituting the current values of count_2 and count_1, we compute count_2 equals 9. This means that by the end of this sequence, there are 9 special subsequences, and the final output for nums equals 0, 0, 1, 2, 2, is count_2 equals 9. Moving on to the third example, nums equals 0, 1, 0, 2, we once again initialize all counters to 0 and proceed step by step. The first number is 0, so count_0 is updated to 1 using the formula count_0 equals 2 asterisk count_0 plus 1 %mod. The second number in this sequence is 1. Using the formula count_1 equals 2 asterisk count_1 plus count_0 %mod, and with count_0 currently at 1, we calculate count_1 to be 1. The third number is another 0. Each 0 can extend all subsequences ending in 0, so we update count_0 using the same formula, resulting in count_0 equals 3. Finally, the fourth number is 2. Using the formula count_2 equals 2 asterisk count_2 plus count_1 %mod, and substituting the current value of count_1, we find that count_2 becomes 1. Thus, for nums equals 0, 1, 0, 2, the final output is count_2 equals 1, representing one special subsequence in this case. To analyze the time complexity of our solution, we note that it iterates through the input list nums exactly once. This means that for a list of size n, we have a single loop running n times. Within each iteration, we perform constant time operations such as updating one of the three counters, count_0, count_1, or count_2. These updates involve simple arithmetic operations like multiplication, addition, and modulus, all of which take O(1) time. As a result, the total time complexity is determined by the number of iterations, each taking constant time. Mathematically, this translates to O(n), where n is the length of the input nums. In summary, the algorithm processes each element once, making it efficient with respect to time. Now, let's consider the space complexity. The solution only uses three variables, count_0, count_1, and count_2, to track the counts of subsequences ending in 0, 1, and 2, respectively. These variables require a constant amount of memory, which is O(1). Importantly, no additional data structures are used, and no recursion is involved, so there is no extra space consumption beyond these three counters. Although we do read the input list nums, it is not modified or duplicated, so its memory usage is not considered additional space. This gives the solution a total space complexity of O(1). Moreover, the time complexity remains O(n) across all scenarios, whether best, average, or worst case, since the algorithm processes every element of the input list exactly once, regardless of the values within the list. Comparing this optimized approach to a brute force solution highlights its efficiency. A naive method would involve generating all possible subsequences of the input list. Since a list of size n has 2 to the power of n subsequences, this approach would require O(2 to the power of n) space just to store them. Additionally, checking each subsequence to determine if it is special would take O(n) time per subsequence, resulting in a total time complexity of O(n*2 to the power of n). By contrast, the current solution avoids generating subsequences altogether. Instead, it counts valid subsequences in a single pass using dynamic programming principles. This reduces the time complexity exponentially, from O(n*2 to the power of n to O(n). Similarly, the space complexity drops from O(2 to the power of n to O(1), as we only track three counters instead of storing all possible subsequences. Finally, we can mathematically confirm the big O notations for both time and space complexity. For time complexity, the loop iterates over the input list nums exactly n times, and each iteration involves constant time operations. This results in a total time complexity of O(n). For space complexity, the algorithm uses a fixed amount of memory to store three counters, count_0, count_1, and count_2. No additional data structures or recursive calls are involved, so the space complexity is O(1). To summarize, the optimized solution achieves linear time complexity and constant space complexity, making it a highly efficient alternative to the brute force approach. When solving this problem, there are a few common mistakes you need to be mindful of. First, incorrect handling of edge cases is a frequent pitfall. For example, forgetting to test for empty arrays or single-element arrays can lead to runtime errors or incorrect outputs, so always ensure you account for these scenarios explicitly in your test cases. Next, relying on an inefficient brute force implementation is another issue. Generating all possible subsequences without pruning unnecessary paths can quickly escalate to exponential time complexity, such as O(2 to the power of n), which is not practical for larger inputs. It's crucial to optimize your approach where possible. Another mistake is misunderstanding the problem constraints. Overlooking details like the array size limit, such as n being up to 10,000 for this problem, can cause your solution to fail when scaling up. You must verify that your solution aligns with the problem's time complexity requirements. Finally, there's the issue of incorrect subsequence construction. A subsequence doesn't require elements to be contiguous, unlike a subarray. Confusing these two concepts can lead to faulty logic in your solution, so always ensure you're clear on the distinction between subsequences and subarrays when implementing your approach. Now, let's discuss more potential pitfalls and insights to help you succeed. One common mistake is re-implementing standard algorithms unnecessarily. For example, instead of writing your own error-prone solution, you could leverage well-known techniques such as dynamic programming or prefix sums to streamline your implementation. These techniques are robust and reduce the likelihood of mistakes. Speaking of dynamic programming, recognizing patterns within the problem is a key insight. Many subsequence-related problems involve overlapping subproblems, making dynamic programming an effective approach. Additionally, focus on optimization. If your brute force solution is inefficient, consider strategies like memoization to store intermediate results, binary search to narrow down potential candidates, or greedy algorithms to simplify the process. When in an interview setting, it's also important to communicate trade-offs clearly. If you begin with a brute force approach, briefly explain its limitations and then outline how you plan to optimize it. This demonstrates a structured thought process. Lastly, always be prepared for follow-up questions. For instance, the interviewer may ask you to adapt your solution to count subsequences with specific properties, such as those divisible by a given number or those that must be in increasing order. Anticipating these variations will make you a stronger problem solver. To deepen your understanding, it's helpful to explore related problems that share similar concepts or techniques. One such problem is the longest increasing subsequence, or LIS, which is LeetCode problem 300. This problem focuses on finding the subsequence with increasing order and is often solved using dynamic programming or binary search for efficiency. Another variation is the number of longest increasing subsequences, problem 673, which builds on LIS but requires you to count all valid subsequences that achieve the maximum length. There's also the distinct subsequences problem, or LeetCode 115, where the task is to count how many subsequences of one string match another string exactly. This problem highlights the importance of careful subsequence construction. Lastly, while the subarray product less than k problem, LeetCode 713, involves subarrays rather than subsequences, it shares optimization techniques like the sliding window pattern, which can sometimes be adapted when working with subsequences. Studying these problems will help you recognize recurring patterns and apply appropriate techniques more effectively. Finally, let's explore some alternative approaches that can be useful for solving subsequence-related problems. Dynamic programming is a powerful technique that trades off time efficiency for space or computational complexity. While it's generally more efficient than brute force, it can sometimes require n² space or time, so defining the state carefully is crucial. Another approach is using binary search with preprocessing. This is particularly useful for problems with sorted input or specific properties, allowing solutions to achieve n log n complexity. However, it does come with added implementation complexity, so it's important to weigh the trade-offs. Greedy algorithms can also be effective, especially for problems where you're trying to maximize or minimize certain subsequence properties. While simpler to implement, greedy solutions may not always work for all variations of the problem. Lastly, backtracking with pruning is a viable strategy for smaller input sizes. By eliminating irrelevant branches early in the computation, you save time and focus only on relevant possibilities. Each of these approaches has its strengths and weaknesses, and choosing the right one depends on the specific constraints and requirements of the problem at hand. Great job following along. To recap, we covered problem number 1955, discussed the brute force method, and worked toward an optimized solution. Remember to practice similar problems to strengthen your understanding. Thank you for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!